So the first speaker is Martha Lewis, who will talk about towards logical negation in compositional distributional semantics. So go ahead, please.
Okay, thank you very much, Joachim, and thank you very much for accepting this paper to be presented, and also to the organisers for organising such a great conference. It's been really my first experience of a full online conference, and it's a lot of fun. So yeah, so I'm going to talk about logical negation for compositional distributional semantics. And I don't seem to be able to put, oh, there we go. And so to talk about this notion of logical negation, I'm going to introduce a concept called hyponymy, which I'll talk about in a minute, and then I'll talk about the compositional framework that we work in to kind of model words and meaning. And the approach that we use is to model word meanings using positive operators. So I'm going to talk about, well, what those are, how we use them to model this notion called hyponymy, how we can build them out of data that we have available for word meanings, and how we can compose them as well. And then I'm going to finally get round to talking about negation and how we can model that and how it interacts with this notion of hyponymy and composition. So all modelling and experimentation in this work has been done in English. I imagine it probably lifts to other languages as well, but if people want to take that forward, that would be nice. Okay, so one question is how can we represent meaning? And one very successful way of representing meaning at the moment is by modeling meaning, word meanings as vectors. So the way that we model word meanings as vectors is we look at a big corpus of text, and we look at how the words that we want to model co-occur, that is kind of occur next to other words in the text. So here we've got this notion, this word iguana, and it occurs close to smelly 10 times and scaly 15 times, but not so often next to teeth and cute. And this gives us a kind of vector of parameters that we can use to represent the word. And then what we hope is that words that have similar meanings are then close together in a vector space. So that's fine, but vectors don't have a whole lot of structure. So first of all, there's no clear way of composing vectors together. So down here on the bottom left, there's a kind of very logical, formal semantics approach to composing word meanings. And they also, they don't occupy, they don't have any kind of internal structure to them, really. So another way of modeling meaning is that you might think of words as being kind of regions of a space, and then you get these notions of containment. And that kind of notion of containment is useful when you start thinking about the fact that words and concepts are hierarchical. So this little tree here is an excerpt from a database called WordNet. So at the top there we've got tableware, and underneath tableware you've got crockery and cutlery. Underneath cutlery you've got fork, salad fork, spoon, dessert spoon. And you can see that, so the idea here is that each of these, as you go down in the tree, you get to more and more specific kind of instances of concepts. And ideally, we'd like to be able to model that within our the way that we represent words. Vector-based meanings representations are usually focused just on similarity, and they don't really have a clear means of addressing these hierarchical relationships. So there have been quite a few approaches to actually representing hyponymy. So over on the over on the left here, the top left, this work, Vilnius and McCallum, they represent words as probability distributions over, so multivariate Gaussian distributions within a vector space. And then they show that you can get these kind of containment relationships that you want. In the center here, there's a notion of hyponymy, where hyponymy is basically modeled by saying that for one word to be, so yeah, I should have said hyponymy is this is-a relationship. So we say that spoon is a hyponym of cutlery, cutlery is a hyponym of tableware. And in this model here, we say that one word is a hyponym of another word if they're close together in the space. So animal is close to organism, but the more general word is longer, has a greater norm than the more specific word. Other approaches to modeling this kind of relationship involve using vector spaces that are no longer Euclidean spaces. So here we have a hyperbolic embedding. So embeddings near the center of this circle cover a wider kind of cone than embeddings at the edge of the circle. And a slightly older version as well is to look at something called the distributional inclusion hypothesis. So this says that a more general word is going to occur in more contexts than a more specific word. So if you have a word like mammal that occurs in all the contexts that cat occurs in and more, so it also occurs in aquatic and herbivorous here, then we would say that cat is a hyponym of mammal. We see that mammal is a more general term than cat. Now, all of these things that I've mentioned so far just work at the word level. But another thing that we do with language is we don't just use words on their own. We use full sentences and phrases. And in order to understand sentences and phrases, we compose words together. So as I'm speaking, you're listening to my words and you're forming a sense of what I'm saying through by some function on the actual words that I'm saying. And Manoush Sadrazadeh and Dmitry Kartsaklis came up with a distributional inclusion hypothesis for the tensor-based composition that we're going to use within this talk. So I'll now go on to the kind of compositional framework that we want to work in.
Martha?
So, yes.
Can I transmit a question?
Sure. I can also see the chat actually.
No, you don't have to.
Oh, okay.
You said that the longer vectors are more general concepts.
Yes.
And then there's a question that would mean that more specialized things become closer in this space. Like a very special machine is very close to a very special animal. So can you maybe drop a comment on that?
I think when I say close, it's the angle. It's not Euclidean distance. So then I think the angle is still going to be further away.
Okay,
Sorry,
thanks.
If that makes sense, yeah. Okay, so we want to have a notion of hyponymy, so that we can then start using that as a proxy for entailment. But we also want to be able to compose words together as well. And the compositional framework that we use was proposed by Bob and Manoush and Steve Clark 10 years ago now. And essentially what the idea is to build up a category for grammar, a category for meaning, and then to build a functor that goes from grammar to meaning. The meaning category that they used was FHILB, finite dimensional Hilbert spaces and linear maps. And the grammar category is called PREGROUP grammar. So a PREGROUP is a partially ordered monoid where each element in the set has a left and a right adjoint. And from those adjoints, we get the following inequalities. So we have the unit here as well. And you can view a PREGROUP as a compact closed category by taking these inequalities to be the cups and caps of the compact closed category. And then the tensor is and the duals are the monoid multiplication and the adjoints here. So the grammar that we construct, to construct a grammar out of a PREGROUP, we take a set of atomic types. So we're going to take N for noun and S for sentence. And you then freely construct the PREGROUP algebra on top of that. And you then assign different elements of that to specific words. So words that are transitive verbs are assigned the type N, R, S, N, L. Adjectives are assigned the type N, N, L. And so then a string of words is judged to be grammatical if when you apply the inequalities from the previous page, the cups and the caps, you end up with just the sentence type S. So the sentence "smelly baby cuddles dad" is grammatical because it reduces down to this sentence type S. And we set up a functor from the PREGROUP over this alphabet B to FHILB by saying that the N type for noun is mapped to a vector space for nouns. The S type for sentences is mapped to a vector space for sentences. The monoidal product goes to the tensor product. And the cups, the most important thing really for this is the cups, and they end up being inner product. And so what do we then get? We get this kind of bigger picture where we've got the reductions that the grammar has told us to make on the bottom. We plug in the vectors on the top, and what we find is that nouns and sentences end up being vectors in this vector space N or S, and that words like adjectives and verbs end up being multilinear maps that take in these nouns as arguments and then give you back a sentence. Okay, so that was all just in FHILB, but what we are going to be doing is we're going to be actually representing words and phrases with positive operators. And the reason we're going to do that is because there's a nice ordering on positive operators which we can use to represent hyponymy. So the first two bullets there are just the definition of a positive operator. Now what we can do is if we've got a word vector V, so let's say over here we've got this word baby, so let's say we've got a vector for baby, then we can lift it to the projection matrix V and V that's associated with that vector. So cat goes to cat with tensored with cat. And then what we want to do is really represent the most specific terms in our vocabulary as just these projections or rank 1 projections. And then we want to represent more general terms as sums of these more specific terms. So a more general term like pet is going to be a sum of all the things that can be pets, so dogs, cats, tarantulas, and so on. and these coefficients P have got to be positive. And you can also make some other choices about what those P's, what properties those P's have, which I'll talk about later. So positive operators have got this natural ordering, and the natural ordering just says that an operator A is less than B if B minus A is also a positive operator. And we're going to interpret this ordering as a hyponymy relation. So what's the meaning category now? So originally we were working in F-Hilb. Now we're going to be working in CPM of F-Hilb. So this CPM construction was, is laid out in Peter Sellinger's work, 2007. And here the category has the same objects as F-Hilb, but the morphisms are now completely positive maps. So completely positive maps look, if you've got a morphism from A star tensor A to B star tensor B, the morphism has to break down and look like this algebraically, or in the diagrammatic calculus it's going to look something like this. So you've got to have this object C that allows you to factor the morphism like in this way. And now we're going to map our noun type to n star tensor n and the sentence type to s star tensor s. The tensor product in this category, so as a diagram in F-Hilb, the tensor product looks like this. Similarly, the cups and caps look like this, but actually it's been shown that that diagrammatically you can basically just draw the diagrams with the thick wires, and essentially you still have a compact closed category from this construction. Okay, so we're going to be working within that category, and so what does this look like? So in the thick lines, you just get exactly the same kind of diagram as before. If we translate that down into F-Hilb, we get something that looks slightly complicated, sort of on the left-hand side like this. But you can sort of rearrange that diagram and you just see that you have this sort of, this kind of neater looking diagram on the side here. So now words are operators, and the composition mechanism is no longer inner product but partial trace. Okay, so again, we've got this this picture here, and now we're just saying that these that words like nouns are now positive operators, words like adjectives and verbs are now completely positive maps on the space, and that the reduction is now partial trace. Okay, so we're going to be working in this sort of environment, and now we're going to talk about hyponymy. So so what we said was that we wanted to interpret this ordering, the Lerfner ordering, as hyponymy, and that said that if we have said that two operators, so an operator A can be said to be less than an operator B if B minus A is itself a positive operator. But then we might want to introduce this might not hold, and in natural language this probably isn't going to hold. So the example I always use is something like you want a dog to be, you might want to say that a dog is a pet, and you want that to be, you want that to come out as kind of relatively true, or fairly true. But obviously there are some dogs that are working dogs, so it's not there's not a complete, you can't, it's not, you can't, there's not a full sort of hyponymy relation there. So in order to deal with that, we introduce a grading, and we introduce the grading by thinking about an error term. So just rewriting this equation here, the fact that B minus A is positive means that B is going to be equal to A plus some other positive operator D. And now if that doesn't hold, then we can introduce an error term into B that kind of adds in just enough to give us back the ordering that we wanted. And we can model this error term in different ways to give different properties to the grading. So in our paper from 2019 with Dea Bankova and Dan Marsden and Bob, we specified that this error term E was going to be some scalar multiple of A. And that does work very nicely, and it has a lot of nice properties, but what it does do is it requires that the subspace spanned by the operator A has to be a subset of the span of B. So in this work, we just do something a little bit more general, where we again have these, so we think about this error term, and I think I've deleted a bullet point that I didn't want to, but essentially we use this error term E, and we kind of compare that error term with A, so that this is 1 minus the size of the error term E over the size of the error term A, the size of the hyponym A. And this makes sense because in this equation, you can always add in A as an error term. So like in the worst case scenario, you have to add the whole of A into B in order to get this order to hold. Here, the lambdas here are the eigenvalues of B minus A. So here you're kind of making a comparison between how many positive eigenvalues there are and how many negative eigenvalues there are in this quantity B minus A. And so those two gradings are what we're going to be using in order to measure hyponymy between two words. So how are we going to build these operators out of data that we have available? So we said that the positive operator for a given word is going to be created by summing together the projection operators of its instances. And so one way to get these is to use some sort of database that tells us which words fall underneath a given concept. We then, so here we would have all of these words, so however many there are, and we would then go to a set of vectors, take the vectors for each of those words, and then build up the positive operator using those vectors. So how are we going to compose these together? So here I'm just going to talk about composing vectors as a kind of motivation for the composition operators that we use. So when we compose vectors together, when we're just working with standard compositional distributional semantics, we have a noun being a vector, being dogs, and then a verb like run being a matrix. So here we've got this triangle dogs, we've got this matrix run, and then we're going to compose them together like this. Now, if you don't want to learn all the parameters for that matrix, you can use various kind of tricks to make a matrix given a vector. So it's easy to learn vectors for words. It's not so easy to learn matrices for words. So one trick that people use a lot, so this is used in work by Manoush Sartrazadeh, Dimitri Katsaklis, and others. So one trick is to take the vector for run and then double it using a Frobenius delta doubling here, and so that then gives you a matrix that you can multiply the noun with. And then another strategy, which also Sartrazade and Ed Greffenstedt used, was actually just to take 2 copies of the verb vector, and then this gives you, if you just tensor together 2 copies of the verb vector, that gives you a matrix as well. So these are kind of strategies for given these easy to learn vectors, how can I make a matrix out of them? So we need to do a similar sort of thing. So what we can do fairly easily is learn positive operators over a sort of given space for nouns. How can we lift those operators up into completely positive maps that we can then use as verb representations? So if we have an operator D, an operator dogs rather, and an operator runs, we can do the same kind of Frobenius doubling to get this to make a CP map that then acts as this this verb representation. And so that's this top one here, which I call mult. So this is just saying that given a noun and given a verb, we're going to compose the verb and the noun together by pointwise multiplying them together. Okay, so another strategy is this thing that I've called B-mult, and I think Bob and Konstantinos call phaser. So I don't know if Konstantinos is talking about that next. But there you take the square root of the verb and multiply it on either side by the noun. And that kind of looks like this, essentially. And then there's one called K-mult, where you take the spectral, so Bob calls this phaser, no, fuzz, sorry. You take the spectral decomposition of the verb, and then the projectors, you kind of multiply the projectors on each side and take a sum. And I'm not sure if this is actually the right diagram for how to do that, but it's something like that. So this P here is a kind of stack of these projectors, and you'd multiply them in and then sum over the to get the right representation. So these are the composition operations that we're going to use. And okay, because I'm running a bit short of time, I'm going to skip over details of the experiments. But essentially what we find is that using these operators and composing words together in simple sentences, we get some nice results that work very well. So how do we start doing negation? So I'm going to go back to thinking about this, just this general way of representing a word as a sum of its more specific terms. And we said that these coefficients P will have to be positive, but we probably want to normalize these representations in some way as well. So you could either take no normalization at all, you could just add a load of stuff together. You could say that the coefficients sum to 1 and then you get a density matrix. Or you could say that we're going to restrict to the set of positive operators whose maximum eigenvalue is less than or equal to 1. So when you're creating these, you kind of divide through by the maximum eigenvalue of the operator. And then if you restrict to this set, then you can do negation in a really simple way. And so all you're doing here is you're taking the identity matrix and you subtract out the word representation. So if W here is just a projector, then this basically sends you to the operator that's the subspace orthogonal to that projector. But W is in general not going to be a projector because these P's can be numbers in between 0 and 1. And so in the paper, I looked a little bit at kind of how this, how entailment strength interacts with this negation measure, this negation operator. And I also looked a bit at how negation works with composition. So certainly when you negate the noun, you get these quite nice representations. When you negate a verb, it then starts to become a little bit more complicated, and you have to, I don't know, so far to get anything sensible out, I've had to sort of say that we have to work in a basis where the verb is diagonal. So there's still some work to do there to sort of see how that's really going. So what did we do to test these ideas? Well, we had a data set that was originally built by Manoush and Dimitri Kartsaklis. And in that data set, you had a set of sentences where you have things like dogs run, entails mammals move. So the first thing to note about these sentences is that you have to think of them as being existentially quantified, because that otherwise the entailment wouldn't hold. And so if you do think that, then you can start adding in negations at various places and then kind of permute the order of the words in the sentence to get like 3 other sets of sentences which have these entailment relations between them. And so the idea is that we build the word representations, we compose them together using various different methods, so molt, bmult, kmult, and what we find is that we do get some fairly good results. So here are the results for this negation data set. So we've got so on noun only, so for a baseline, we looked at just looking at the noun, because actually the way that the data set was constructed was that the nouns are always the nouns should always be you should be able to get the answer just from looking at the nouns. So noun only forms a strong baseline, and here we have that average does pretty well, but also just multiplying does pretty well as well. And then all of these other operators also beat the noun only baseline in at least 2 of the data sets. This is similar, but with a different measure of hyponymy. But here we do always get this significantly better results than the noun only baseline. Okay, so in summary, what I've talked about here is that we have this method for building word representations that reflects the hierarchical nature of natural language and also preserves similarity. And the representations sit within our compositional framework, so we can look at hyponymy at the word level, word to word, and then also at the phrase level, so we can start to use that as a means of entailment. And in order to model negation, we kind of look at it as being a kind of projection to the subspace orthogonal to a concept. So it's not exactly that, but that's the sort of thing we want to look at. And we also find that it does interact pretty well with composition and also hyponymy. So for further work that needs doing is that I don't really know where it ought to sit categorically, because it's not a morphism in the category CPM FHIL. I need to look into more like what the properties of these graded measures are. And actually, we also want to look at other composition operations, because it turns out that the the B mult and the K mult, or the phaser and fuzz, don't actually preserve hyponymy. So I did, like you might think that you want operations like that to preserve hyponymy, essentially. And we've already started also building much more automated methods for building these positive operators. We want to test on larger scale data sets rather than just these kind of single phrase data sets. Make deeper comparisons with other methods in NLP, and actually also, I haven't put it here, but you may have noticed up here that I do some kind of weird things about these non-mammals. Actually, what we'd really like to do is to have a notion of quantification. So you can start negating sentences and then start thinking about how the negation is going to interact with the quantification there. So just before I say thanks, I'll just say, if you like this, shameless plug, there's a workshop on next month, the 6th and 7th of August, which will cover lots of this kind of thing and related. So work like Lachlan presented last Tuesday as well. So thank you very much, and love to hear some questions.
Okay, thank you, Martha. And only if people are muted and can clap, otherwise they can use the icon. So we have time for a few questions. Julio, would you want to speak? Otherwise, I read it. It says, whether sentences with negative concord, things like "I don't go nowhere today" and "you don't know nothing," could be tackled by the model straightforwardly, or do they require some special treatment?
Yeah, oh, I don't know. I haven't really thought about that sort of thing yet. So I guess it would be, I mean, yeah. So the operator as it is like an involution. So one negation would cancel out another negation. So I guess I guess I'd have to think about how that should work. Yeah, I don't have a. I think it would might need some kind of special treatment. Yes.
And here's another question from Lee Monshine. Could professional antinomies provide useful basis for experimental evaluation of hyponymy constructions?
There's an error in the typing. I meant ontologies, not antinomies, but my typo, my machine interpreted ontologies as antinomies.
Yeah, so WordNet is, which I built these from, is a kind of an ontology. And actually a student of mine was doing some work on using the Microsoft concept graph to build these kinds of operators. So yes, I think these, so yeah, ontologies would be useful for building these sorts of things.
Oh, I'm wondering whether they would be useful for assessing, the performance of hyponymy constructions.
Oh yes, yeah, also that too, yeah. So if we built them from some other means and then assessed them according to some ontology, yeah, that would certainly be a good way of looking at these. Okay,
I think we need to postpone further questions to later on, either in the Zulip or maybe in one of the breaks. So let's thank Martha again and move on to the next talk.
Thank you.